Good afternoon, everyone. Today I'm going to talk about symmetrical components and use this as an opportunity to demonstrate a small computer program that I have written which allows us to do some calculations using symmetrical component techniques. Symmetrical components is of course a standard analytical tool used by power systems engineers to calculate the voltages and currents which appear on a power system during fault conditions. There are a number of textbooks which deal very effectively with the calculation, and this program includes data sets from two of these textbooks, the one by Anderson and also the one by Stevenson. And for the purpose of this demonstration, I'm going to use the data set for the sample calculations which are provided in Stevenson's textbook. So here we see the results of the calculation for a line to ground fault on a power system using Stevenson's sample dataset. The first thing to note is that the positive, negative and zero sequence impedances have no real part. In other words, the impedances are wholly imaginary, i.e. they are just reactive. And the fault impedance is zero. So as a result of this, when we calculate the line to ground fault current, we observe that the current in the faulted phase lags the positive sequence voltage by 90 degrees due to the fact that there is no resistance in the network. The voltage on the faulted phase, the red phase, phase A, is zero. We can see this in the phasor diagram, and we have high volts on the two unfaulted phases. Looking at the time domain wave shapes, we can see this. We have voltage on the two healthy phases and we have 0 volts on the faulted phase. Similarly, we have 0 current in the healthy phases and fault current, in this case 6 kA peak, in the faulted phase. 6 kA peak is of course about 4.28 kA RMS. The theory of symmetrical components tells us that the sequence components of current will be equal for a line to ground fault, and that is shown in this phasor diagram here. The sequence component of voltages will not be equal because they are determined by the sequence impedances multiplied by the corresponding sequence current. But note, for this earth fault we have a strong zero sequence, shown in green, component of voltage. In addition to the phasor diagrams and the fault waveforms, we get a tabulation of a number of quantities in terms of magnitude and angle. So we get the currents in each phase, we get the sequence components of current with respect to phase A, we get the voltages in each phase, we get the sequence components of voltage with respect to phase A, and we get the line to line voltages. In addition, we get the ratio of the negative to positive sequence voltage. In other words, a measure of the negative sequence unbalance on the power system. We get the ratio of the zero sequence to positive sequence voltage. We get 3 times the magnitude of the zero sequence voltage. That is the polarizing voltage, which would typically be used to detect an earth fault. And we get 3 times the zero sequence current. And because this is an earth fault on a single phase, 3 times I0 is equal to the current on the faulted phase. So these results display the typical features which we would expect from a bolted zero impedance fault between one phase and ground. We can look at what happens when we have a phase-to-phase fault. Now, for a phase-to-phase fault, because there is no flow of current through the earth, the zero sequence components are zero. So we have zero sequence voltage is zero, we can see this in the phasor diagram, and the zero sequence current is zero, we can see that in the phasor diagram. Because we're effectively connecting 2 phases together, then the voltages on 2 phases are equal, and the voltage on these faulted phases is reduced, and we have healthy volts on the unfaulted phase. And we can see that in the tabulation here. VA and VB are equal and low, and VA is high. Because we're connecting 2 phases together by a zero fault impedance, the fault currents are equal and opposite in the phases, and we have no fault current on the unfaulted phase. And we can see this in the phasor diagram. Equal and opposite currents in the faulted phases and no current in the unfaulted phase. We can also see from the sequence component phasor diagram that the positive sequence current and the negative sequence current are equal and opposite. Finally, we can look at the double line to ground fault, and now we see that for this set of parameters we get a very strong zero sequence current, and the zero sequence voltage is equal in magnitude to the positive sequence voltage, which is also equal in magnitude to the negative sequence voltage. And this is what we would expect for this fault, because the method of symmetrical components tells us that the positive, negative and zero sequence networks have to be connected in parallel. If they're in parallel, then the voltages must be the same. So this calculation can determine the sequence components of voltage, current, and it can also draw the time domain wave shapes. Now, one of the things I was interested in was the sensitivity of these sequence parameters to the input data. So let's just go back to the line to ground fault. And the fault resistance is 0. We have a purely reactive network, and the fault current lags the positive sequence voltage by 90 degrees, and the voltage at the fault on the faulted phase is 0. What happens to these quantities as we increase the fault resistance? In other words, we transit from a bolted three-phase fault to a high resistance fault. Well, we can investigate this by changing the input value of ZF by simply clicking on this slider and observing the phasor diagrams and the current and voltage wave shapes. So we're now increasing the resistance. You can see that the current phasor is swinging round and is now in phase with the positive sequence voltage, more or less. So there's the current phasor. It's now swung round from 90 degrees and it is now almost in phase with the positive sequence voltage. And this is to be expected because now the dominant impedance is the high resistance of the fault. The voltage at the fault was initially 0, and that has now increased to a value of just short of 1 per unit. And you can see this in the faulted waveforms. Before this voltage was 0, now we have healthy volts, or at least we have volts on all three phases. The clue to what is happening on the power system from the point of view of sequence components is, of course, the polarizing voltage. We can see here that 3 times V0 has now risen to 13% or 0.13 per unit, and that's a type of signal which would be used by the protection system to pick up a high resistance fault on the network. If we look at the phase-to-phase fault, then with our high impedance or high resistance fault, then we no longer see the voltages on 2 phases being equal. Because this is a line-to-line fault, the zero sequence component is 0. So there's the zero sequence current, the green dot is at the origin, and the zero sequence voltage is 0, it's on the origin. We still have equal and opposite currents in the faulted phases, but the voltages on the faulted phases are different. But if we now decrease the fault resistance, so we push it back down towards 0, we can see that eventually, as the fault resistance gets smaller, we get back to the situation where the voltages on the healthy phases are equal. So that demonstrates how we can use this program to investigate the dependency of the sequence component voltages and currents and fault waveforms on the input parameters. I hope you found this brief video interesting, and those of you who work with me will be able to obtain a copy of this program